Well, let's look at one of my favorites, ideal gas law. Reason I like this as a favorite is because it all kind of comes together, and this deals with gases. So when you think of pressure and volume of a gas, that is equal to the amount of gas times this gas constant, it's just a regular, times its temperature. So this illustrates a lot of relationships dealing with gases, which is very different than with solids and liquids. So let's start to take a look. So the nature of gases. They expand to fill their containers. They don't just stay at one place. They're not like liquids. They don't just stay in a chunk like solids. They're fluid, meaning they move. That means moves in a room, moves across a container, and so on. Very low density. Compressible, meaning there's a lot of empty space, and they effuse, which means to go through a tiny hole. Think of like a leak, right? You might have a little leak in a plastic bag with water, but it won't actually go through all that much or very quickly. However, gases will go right through any small hole. And diffuse, meaning that they have ability to spread. So this is kind of the unfortunate side that when someone has a toot, that across the room you'll eventually get a whiff that they let something go because of the fact that these gases move and diffuse all on their own. Unlike if someone dropped something down like some urine or something, that's not going to go across the room and get you wet. However, you might smell it because, again, those components of urine that are what we consider the smell of urine will diffuse throughout the room and you'll be able to smell it. Again, gases are different. Now, pressure is something that's a little different when we think of anything else that's considered to be objects. So we think of something solid, like I got this remote here. It's putting pressure on my hand by its surface that it's in contact with, right? And so if I put it narrower, it still has the same mass, but now it's a smaller area, so it's exerting more pressure on my skin. Nothing damaging, though, of course. So that's why we think of it's equal to the force over unit area. We have some units, usually called a Newton per meter squared, and we call those pascals. So they kind of gotten a derived unit, a complex unit, and then change it into a simple one. Science likes doing this, even though it can kind of make it confusing. We have some conversions that you're going to likely see that you might have to do from time to time, but these are also on your AP, the AP constants that are on the back of your periodic table. So they're there for your assistance. So we've talked a little bit about STP, standard temperature and pressure. 1 atmosphere is the pressure, or 70-60 torr, both equivalent. Again, these are different units, but mean the same things throughout. 0 degrees Celsius, 273 Kelvin. Molar volume, 22.4. You could add the 2 if you want. Liters at STP. So this is the only things you can do at STP. Anything else, temperature different, pressure different, you got to do the whole ideal gas law. Standard molar volume, again, all the volumes of gases at same temperature and pressure contain the same molecules. This will allow us to do a few different things. At least something that we used to do back in chemistry is do equal volumes. So we used to use what are called volume ratios, much like mole ratios are with stoichiometry, because if 2 liters of hydrogen and 1 liter of oxygen make 2 liters of H2O, all of those volumes are interchangeable, just like moles. It's the exact same process, only switch out moles with liters. I hadn't seen that much too in AP, but it is a standard chemistry practice, so they can always throw that in on one test, give or take a year. As far as where this all comes from, you throw in your values. You can do this long term of ideal gas law, and as long as you plug in the values that you would normally put in, you get your 22.4 liters. Why is this important? I don't really know. You don't conduct, 1 atmosphere is pretty close to what we conduct in a everyday life setting. But 0 degrees Celsius, I'm pretty sure I don't work in 0 degrees Celsius. I'm not a freezer. But I think it's just to give a grounding that there's this relationship between the two, kind of like an introductory to ideal gas law, because it can be confusing or complex. So the kinetic molecular theory, you probably recall a little bit from backwards in chem, and I either am going to move it ahead of this one or right after. They're related to the idea of talking about how gases work. So some of the concepts, the gases consist of small particles very far apart. So because they're very far apart, it means there's a lot of empty space. Collisions between them and the walls of the container are elastic, meaning there's no loss of kinetic energy. There's no transfer to the things. There's no cooling of it. They remain perfectly balanced in their energy. Gas particles are constant rapid motion, therefore possess kinetic energy, the energy of motion. So they're always moving. No forces of attraction or repulsion between gas particles. This one's a huge one because a lot of particles are polar. We just talked all about the intermolecular forces, where you'll always have some polarity, whether it be polarizability. That's the one I had struggled with. It will have the idea of an induced dipole, a permanent dipole, an ion dipole. There was always going to be something. In addition to gravity, gravity we don't mention, I think more because we're in chemistry, not physics. However, there's always going to be some force of attraction, but kinetic molecular theory says, hey, guess what? There isn't. And the last part is that the average kinetic energy depends on temperature, not what the particle is. So the idea is kinetic energy is 1/2 times the mass times the velocity squared. Now, you have different masses of atoms, but what ends up occurring is that whether you have something a big heavy atom and a very tiny atom, if they're at the same temperature, they have the same kinetic energy. They don't have the same speeds, but they have the same kinetic energy being at the same temperature. So that was just a little precursor of kinetic molecular theory. I'm sure I'll talk about it a little bit more in depth in the next section. Now, doing the calculation components. Pressure, volume, moles, gas constant, temperature. Pressure in atmospheres, liters, moles. Remember moles and molar mass, or I should say mass and molar mass is equal to moles. You know those relationships from our conversions. R holds closely when pressure is very close to 1 atmosphere, so you might have some multiple choice questions that come up in referring to 0.99 atmospheres. You can roughly say, hey, it's going to be close to STP. Proportionality constant, you've got the ones that are on the periodic table from your AP. You really won't have to do conversion, maybe for some problems here or there, but essentially stick with what you have there and understanding the relationship. And then temperature, is in kelvins. So you always have to convert to kelvins, not in Celsius or Fahrenheit, for God's sakes. No. Getting the other gas laws. You don't generally have some direct questions about these different gas laws, but you will have to demonstrate some illustrations between volume and pressure, volume and temperature, and volume and moles. All right. So when you have all of these, you get these different gas constants, get these different relationships, which we'll utilize and look into. So starting off first with Boyle's. One of the things they love doing is giving you graphs on the AP test and wanting you to get some information from it. So this is the true sense of gases with pressure. So when pressure is very tight, it's going to be at a very high volume. Low pressure, low amount of pressure, very high volume for the fact that it's very spread out. It can't exert a whole bunch of force on the surface of the container if the container is so large. The smaller the container, the much higher the pressure can be, because again, the surface area inside is going to shrink and shrink, which is going to be decreasing that surface area that force, which is the pressure, is going to be exerting on. It's an indirect relationship. As those decrease, kind of like what I was just saying here, that there's this relationship of proportionality. So when the pressure doubled, that's because the volume shrunk. One of the things that students often want to say, which is a little inaccurate, is the fact that the pressure, the volume shrunk in half because the pressure doubled. Pressure is actually more of a consequence of volume change. If you wanted to increase pressure, you would decrease the volume. If you wanted to decrease the pressure, you would increase the volume. You can't really increase pressure at a constant temperature by changing anything. Really, only volume can change. And because of that change in volume, you get a change in pressure. It's different when you have something like a change in temperature. Charles' law, volume and temperature. With Charles' law, volume and temperature, the temperature increases, the volume increases. Now, this is if you have a flexible membrane. They always go with balloons because we all have this relationship that balloons will expand pretty easily. They always have a breaking point, but this would be before that. Of course, before the temperature of it would melt and also decay the balloon. But as we increase, This is a little slightly different because on this one, they look at the idea that at a certain temperature, looks like a little bit, a skosh before 500 degrees Celsius, more moles is going to have a bigger volume. That makes sense, right? That the idea is that as you have more gas in there at one temperature, you're going to have more particles exerting force. Therefore, you're going to be able to increase that if it's a constant pressure. So therefore, same energy, same pressure. Because we have more moles, the volume will get larger. What this is really trying to illustrate, though, is that 1 mole, as we increase the temperature and leave constant pressure, the volume is going to increase. Very direct relationship and very proportional relationship. Although I will say this doesn't look like it's, well, yeah, a little over. That's probably proportional. So they're all very proportional to each other in the sense of what you do with each of these volumes. If you go back to 0, this is where you get absolute 0, to where you'd have no motion of anything else. These can't really be measured exactly because they go into liquid, so they're no longer in gas form. So therefore, their attractive forces become very different in how they come together. When we see this again, all our little atoms being present, and I told you they love balloons, it'll expand due to the increased temperature, because as they increase temperature, they increase kinetic energy, they increase kinetic energy, they increase force, they increase force. Now, if you have a constant pressure, that means if force goes up, volume has to equally go up, or surface area, the interior area of your volume has to go up at the same amount in order for pressure to be the same. So that's why the balloon will swell when you increase temperature. It'll decrease when you decrease the temperature. Avogadro's law. So this is looking back what we looked back just a few slides ago, that when you have more gas, you're going to have a bigger volume. Duh. When you have a smaller volume, you have less gas, as long as temperature and pressure are all the same. So this is a very direct, I think, very simple concept to understand. You know, when you go from, where's a nice one on the line? These are all kind of poopy. You know, when you're right here at 9, when you double it, you get about 18. You know, these are all very proportional concepts, but you need to work with them not only in a mathematical standpoint, but also in a way to explain standpoint as well. Constant temperature and pressure increases, you have more moles. When you have more moles, you're going to increase the force because you have more particles. Increasing the force increases the total pressure, but when you leave the pressure to be constant, that's going to increase the volume. A very linear, direct relationship. So this leads us into partial pressures. So with partial pressures, this is just the idea that the pressure of all the gases within a container is a sum of the individual components. This makes a lot of sense, much like when we go back to my idea of pressure on my hand for my remote, that if I were to add something like my sunglasses as well, hey, the pressure of those together is going to be the same as this one individually and this one individually put together. So same idea, not much of a big leap by any means. However, this plays a role when we think of collecting gases, because there's a role that's been traditionally very common of collecting gases over water. When you collect a gas over water, there's always water vapor present. So we often think of at room temperature, anywhere in between freezing and boiling, we often think of, well, water's liquid. Water exists at all components, I should say at all components naturally on Earth. However, from 0 to 100 degrees Celsius, there's also water vapor. We know this from humidity in the air. It doesn't have to be 100 Celsius to have water vapor. You see clouds up in the sky, and that's not 100 degrees Celsius up there. So when gases are collected over water, and this is a chemistry's favorite, much like a children's favorite's mac and cheese, this is the mac and cheese of chemistry. The idea is that you're going to see these values. Of course, they'd be given to you. You're going to see them in problems. You're going to do it in a lab will do. You're going to do it guaranteed on the AP exam in one way, shape, or form. You have to subtract out the amount for the water vapor pressure because, like I said, if you measure the pressure of the container to be 1.2 atmospheres, one of those pressures is water vapor. And depending upon the temperature, it can be significant. It can be quite significant. This one's given in millimeters of mercury, but it's one that you want to subtract out to not account for the pressure of the water. A couple things of math I've kind of talked about a little bit before. Mole fraction, ratio of partial pressure. So they might say that, what's the percentage of pressure that water's given in this problem? You essentially, just like any other kind of ratio, you take the smallest amount over the total, and you got the mole fraction. Again, moles over moles, moles over moles. All these relationships are pretty common when you think of fractions, and especially when you think of back to conversions. So the partial pressure is a mixture of these things. One of the things that comes up is percentages. So when you think of nitrogen has 78% composition of air, find its partial pressure. Well, that's going to be the idea of 1 atmosphere. It's going to be 0.78 atmospheres. So taking this idea of 100% is, again, this idea of this ratio when it's divided. And we'll talk about this next time. So as you work on these and go through these, let me know what kind of questions you have, and I'll catch you later. Take care.